Okay, so this lecture we're going to talk about linear regression and a little bit about subset selection. And part of this lecture is taken or is sort of drawn inspiration from the Elements of Statistical Learning by Hasty, Titfrani, and Friedman, Chapter 3. If you want, read this in advance. These next two lectures are going to go over that. And this is Statistical Machine Learning, and I'm James Sharpnack. Okay, so let's go back over linear regression here. In linear regression, we have P predictor variables. These are columns of X. The X is the design matrix, so we're typically going to be using matrix notation throughout this lecture. And N are the number of samples, so that's the length of the Y vector and also the height of the X matrix. And we're going to fit ordinary least squares, which solves the following on the training set. So if X transpose X is invertible, then we invert it, and then we multiply that by X transpose Y. And that gives us our beta hat. And X and Y again, N by P, and N arrays. So this all makes sense. It's always good to check your dimensions. So of course, X transpose X is P by P, invert it, another P by P matrix, hit that with a P vector, because we had a P by N matrix hitting an N vector, which gives you a P vector. So all the dimensions work out. You get another thing that's P dimensional. So implicitly what we're trying to do here is solve the normal equations, which is this X transpose X times beta hat is equal to X transpose Y. Okay. And actually, before we go into that, I'd like to just reiterate that this X transpose X times beta equals X transpose Y, there's always some solution to this normal equation, as long as you can write it out and it all makes sense. But it doesn't mean that this matrix is invertible, and the solution might not be unique, right? So this can happen quite a bit. Okay. So now, if we're given a beta hat, we can predict. So we have our fit and our predict method. Say we apply predict to the training set, right? This isn't sort of kosher if we want to try to assess our test error, because then if we're overfitting, then our training error and our test error can be very different, right? And we saw that with the countries data set before. If we apply predict to the training set, then we have that our Y hat, we think of this as now as a vector, is just equal to our X times beta hat, right? And we can write this out. So this is sort of standard linear models methodology, is if we write this out, what the solution to beta hat was, assuming that this X transpose X was invertible, that gives us something that's X times this X transpose X inverse times X transpose Y. Right? And one way that we can think about this, if you remember your linear models class, is that this is a projection of Y, which is a vector, an N vector, onto the column space of X. Right? And we'll talk a little bit about what that means. But it's very helpful to have this sort of in your mind. This is what predicting on the training set is actually doing for ordinary least squares, for linear regression. And notice this is a projection in n-dimensional space. It's not p-dimensional space, it's n-dimensional space. So it's sort of something that gets bigger as the number of samples increases, which is a bit odd sometimes for people. So one way to validate that this is a projection is just to check it mathematically that it's idempotent, which just means if you take p, multiply it by p, then you get back p, right? And if you just look at what p is, it's this projection matrix here. It's n by n. This X times X transpose X inverse times X transpose, right? We just plug that in to P times P. We see that we have this X transpose X here. It gets hit with this X transpose X inverse. And so these two become the identity. And then we just end up getting P back. So this is a projection. And what really does that mean? So one way that we can visualize this, I stole this image from Wikipedia. So that's the credit. If we can visualize this as we have our column space of X, which, remember, each column is an n vector, just like y is an n vector. So this is n-dimensional space, where n is the number of samples. And so we have x, the column space of x, is some lower dimensional space, possibly, than p, right? So, or than n. So this is a p-dimensional space, and at most a p-dimensional space in n dimensions. And if p is smaller than n, then you have that. You're probably going to have that y doesn't lie exactly within this space, unless, you know, if you have some noise, then this is going to happen. So the projection onto the column space of x is going to project this y vector onto this column space of x. And if we look at that y hat, which is this x times beta hat, this y hat is that projection onto this column space of x. Right? And one way we can think about that is that we're going to try to reconstruct y using just columns of x. So we're going to do our best, right? We have the columns of x to work with, and we're going to try to reconstruct y. So what we do is we take x1, which is the first column of x, and we multiply it until it sort of gets as close as possible to this y, right? Which is here. And that quantity that we multiply it by is our first coefficient, beta 1. Right? And then we do the same for x2, we get beta 2. And then we have this vector y hat here, which is the sum of these two. And that's the projection of y onto this column space of x. So that's the geometric intuition for what's going on in ordinary least squares. It's very helpful sometimes to think about it as a projection onto some column space, because then sometimes you can figure things out without actually having to do a lot of matrix algebra. Okay, so this leads us to our first exercise. Suppose that we have a perfectly reasonable n by p design matrix X. So this is the sort of thing that's invertible, p is less than n. All the usual things that we assume is true about linear regression is true in this case. And then we have an n response vector y, such that x transpose x is invertible. Right? So it's nice. And now we suppose that we duplicate the columns of x. Right? So this could happen if someone was encoding these variables and they accidentally created one twice. Right? And then they did it for all of the variables for some reason. Suppose that we duplicate the columns of x to make an n by 2p matrix, right? So now there's twice the number of columns that we had before. And suppose that we want to run ordinary least squares with the new data by finding solutions to the normal equation. So it turns out that if you take this new design matrix, which we'll call, say, x tilde, that it doesn't have a unique solution. So I'll tell you that right off the bat. Right? But it's still, you can still think about solving the normal equation, just finding some solution to the normal equation. And suppose that this normal equation, the solution, is still doing some sort of a projection. It's just not exactly clear what this, it's just not exactly clear how to get this projection matrix using the inverse of x transpose x, because now it's not invertible. I won't tell you how to do that right off the bat, but we're just going to work with the normal equations, and I'm just going to tell you that x hat is still a projection onto the column space of this new design matrix. So the first question is, using this intuition, what is the impact on y hat? Right? The second question is, we have this normal equation, that always exists, and so we can show that, so I want you to show that a valid solution to this new normal equation is beta tilde, where beta tilde is just 1/2 times beta hat stacked on top of 1/2 times beta hat. Right? So, you know, beta tilde is supposed to be 2p, and so there has to be two copies of beta hat if we're going to use beta hat, right? Because it's a p vector. And so this gives us a 2p vector. And when I use this semicolon, I mean that they're stacked on top of each other. Each of these corresponds to one matrix on top of the other. And now, in general, you can try to guess what form do other valid solutions take. And you can go back through number 2 for all of those forms. So do this exercise. It gives you a pretty good intuition of what happens when the x's are collinear. And now we're going to, after this, we're going to talk about, well, what happens if they're not exactly collinear? We don't have the singular design, but they're approximately collinear. And that'll lead us into why we want to do things like regularization.